Wanted to wrap up what we did in lab, and this is where we were. So when forces are balanced in the case of our elevator, we have the normal force going up, and we have the weight force going down. And these arrows, if I draw them right, would have the same length. What we realized was the normal force and the weight cancel each other out. That's what it means when the forces are balanced, and the way we write that is like this. Now, many of you I saw on the lab actually ended up writing it a little bit differently. I saw people do this. And that's totally fine. It's the correct answer, but I'm moving to this way of viewing things because I want to contrast it with the equation that we came up with in lab that was new, which is what happens when forces are unbalanced. When forces are unbalanced, we have the normal force going up, and we have the weight going downwards. But the effect of these forces is that they no longer cancel. What we actually learned and what we discussed, really, you actually showed me this, is you realize, hey, wait a minute, if the forces aren't balanced, that means the object is, so when they're balanced, it's moving at constant velocity, or it's at rest. So if an object is not doing either of those things because the forces are unbalanced, the only thing it can be doing is accelerating. So what we realized is that the normal and the weight in the case of the elevator accelerating means that what's happening is the mass is in fact accelerating. So we get a very simple idea. When forces are unbalanced, what happens to the mass? It accelerates. So you just multiply those two things together. And this is what we call Newton's second law. Now, I talked a little bit about a more general thing where I said, well, whenever you have any system, when you got some box on the floor, some friction force, and all this stuff, or, you have a person who's being fired out of a cannon, and they have like rocket shoes, and they're flying through space, and there's the force or the thrust from the rocket shoes, and there's gravity, and I don't know, there's air resistance, and all this other stuff. Even in this case, there's a way that we can add up all these forces. And when we add up all these forces, regardless of what we call them, we're going to use a term called F net. And that means the total force. We'll introduce that a little bit more next week. This week, I want to focus on this and take a look at the problem that I want you to do. So here we have an elevator that has an acceleration of 0.25 meters per second squared. And take a look at this problem. Read it through before you begin. And let's actually try to set up what's going on. So now that you've read this thing, let me just go back a page and, well, no, you know what? We'll do this. I'm going to use my weight, which is 150 pounds. And when we use the conversion that Mr. Farrell gave us, I think it's 4 point, let me just double check. So the conversion that we have, oh, fiddle up, 4.45. 150 pounds times 4.45 newtons per pound. And that's going to give me about 670 newtons of weight. Just for the heck of it, let's get my mass. Let's remember that the mass is given by my weight divided by the acceleration due to gravity, so that'll be 670 newtons divided by 9.8. And when I do that math, my mass is about 68 kilograms. Awesome. Now, here's what we want to do. We want to know the normal force. And here's the thing. It's very tempting to say, oh, is this the normal force? Because it's the weight. And here's the thing. We have an acceleration. The answer is no, because now the forces are unbalanced. So if we go back to our previous page, this is balanced. At rest, yeah, they're equal. But now they're no longer balanced, so they're not equal anymore. So let's set up this equation using this new idea. So we're going to take this idea and apply it to this problem. We have the normal force going up. We have the weight pointing down. And the effect is that the mass, my mass, accelerates on this elevator. Now, it says that it has an acceleration of 0.25 meters per second squared when it approaches the top. So let's be clear on this. if I am approaching the top, the 6th floor, and I'm coming near the top and there's an acceleration, that acceleration had better be downwards. Here's what upward acceleration would do. So here's Sacred Heart Cathedral, and there's the elevator, and it's flying into the air, and this is like a close-up of my face on the elevator as I fly through the air, crashing through the roof. I'm praying. And I am flying through the roof if the acceleration is positive. So the acceleration is downward as we're approaching the top, because if it were upward, you would accelerate straight through the top. So this acceleration is negative 0.25. So now let's go ahead and plug in our numbers. We have the normal force, which we don't know, minus the weight, which is 670 newtons from here, equals my mass. And my mass, I got it here, 68 kilograms, times my acceleration, which is negative 0.25. So I can go ahead and solve for my normal force, and that's going to be 670 minus 8 times 0.25. And that's going to give me a normal force of 653 newtons. When you think about it, this makes sense. If my real weight is 670 newtons, my scale should read 653 newtons. And when we check this out with our lab data, all of us got that our scale got a lighter reading. And remember that the scale gives us the normal force. All right, so your homework is to take a look at 4 and 5 and submit the answers to those on the Google Docs.